Okay, so much for theory. We're now going to take a look at some examples, how to apply what we just have learned, especially the concept of motional EMF. Okay, our first example. What I have here is a U-shaped rail. Okay, it's made of ideal metals, ideal conductors, except there is a little resistor here. So all the resistors are concentrated here. And to form a complete loop, I have a metal bar, this red metal bar, which can slide frictionlessly in a vertical plane. Okay, and it's attached perfectly here and there. So you may use a ring here, whatever. So it can slide up and down like this without any friction. Okay. Now, suppose there is a uniform magnetic field that goes into the paper. Okay. In other words, it's horizontal. The vertical direction is like that. Right? Suppose, and then you start the metal bar from rest. Okay. At that moment, we choose an x-axis going downwards, originated at the initial position of the bar. So, as you release the bar from rest, the weight of the bar, which is mg, will pull the bar downwards, right? That is going to cause the bar to cut through these magnetic field lines, thereby generating an induced EMF, right? And that induced EMF will power a current, because there's a complete loop. It's going to power a current, and that current flowing in the bar will be subject to a magnetic force. So the motion of this bar will no longer be simply free fall. It's not going to be a free fall anymore, because there will be a magnetic force acting on it. And that magnetic force is actually a time varying force, because the speed v of the bar is not a constant. Okay, so that is what we can think of. Now, what we wish to find is what is the speed or the position x of the bar as a function of time. Okay, at t equals 0, it starts from rest, it's right here. You know, the initial speed is 0 because that's how we set the system. We release it at 0. It's going to gradually pick up speed, okay, without any magnetic force, without any issue coming from Faraday's law. It's just going to be a free fall, right? V will be equal to gt. So if we were to plot it, it would simply look like this. V of the bar as a function t will be simply a straight line. The slope is g, right? The slope is g. What happens if you consider Faraday's law? You consider the induced EMF and consider the corresponding induced current and corresponding magnetic field, magnetic force on it. How is that going to change the situation? Okay, we need to determine the direction of magnetic force to see if there's a retarding force or is that force also downwards. Okay, let's do that first. Now, we can simply use conservation of energy to determine the direction of the magnetic force. And I can tell you right away, without any further ado, that that force has to be upwards. There simply is no choice. The magnetic force, Fv, has to be up against gravity. There is no choice. Otherwise, you violate conservation of energy. You don't have to know any details about Faraday's law or anything like that. Now, why is that? How does conservation of energy dictate the direction? Well, here, look. Suppose Fv is downwards. Okay, now, doesn't that make it go faster than free fall? So if you compare with the case of a free fall, you'll find that with this additional force, the bar is going to go down even faster than free fall, which means it will get even more kinetic energy than free fall, right? So the question is, who is supplying you with this kinetic energy? Somebody has to pay for it, right? Additional energy. Who is paying for it? What, the magnetic field? It's not doing anything. It's still the same magnetic field. Nothing has changed. It's still the same field. What about this resistor? Well, in fact, there will be current through the resistor. Whether flowing this way or that way, it doesn't matter. It's going to generate some heat, right? Generate some heat. So what you get is that once you have this magical magnetic force going downwards, two things happen. One is the rod is going to go faster. Therefore, you got more kinetic energy than before. And secondly, you're going to generate some heat here, or even you can power a light bulb here, you know. But then you get extra amount of kinetic energy and extra amount of thermal energy, right? You can make the rod go faster and power the light bulb at the same time. How does that add up? Isn't that too good to be true? Well, it is too good to be true. Okay, so in reality, what happens is that the force, the magnetic force, has to be opposed to the gravitational force, so that when you consider the magnetic field, the bar will go slower than free fall. It will not get as much kinetic energy as it would get in a free fall. So you have a deficiency in kinetic energy. But where does that energy go? Well, it goes to pay for the thermal energy released here. That's what happens. Okay, so that is how conservation of energy alone can determine the direction of the magnetic force. Now, of course, you don't have to believe me. You don't have to believe me. You can use Faraday's law to determine the actual direction of the force. Okay. Look at an enclosed loop like this. Okay, you have to look at an enclosed loop or enclosed area. Look at this enclosed loop. As the bar goes downwards, what happens to the flux? It's obviously increasing, right? Because the area gets greater. The flux is inward. Okay, the flux is inward, and therefore the inward flux is increasing, and nature doesn't like that, and therefore nature would then drive and induce current. Is it clockwise or counterclockwise? Well, you do not want to increase the inward flux because it's already increasing. You want to generate an outward flux, up like that, right? And the only way to do that is to promote a counterclockwise current, which produces a flux outwards. So naturally, a current like that would be induced. Okay, so there will be a current flowing in the bar from left to right. Now that current, of course, will be subject to a magnetic force. What is the direction of that magnetic force? Well, recall what chapter is that? That will be chapter 29. Okay, IL cross B. You remember that? IL cross B. What is I? I is the current flow in the bar. L is defined to be a vector along the direction of the current flows. It's from here to there. L cross B. L goes this way. B goes into the paper. L cross B. You get a magnetic force. See, it's up. Exactly as we predicted from conservation of energy. Okay, so that works out. No matter how you look at it, you get a magnetic force going up. Now, with that magnetic flux, a magnetic force, I want to qualitatively predict what kind of motion this bar will experience. Well, the magnetic flux is VLB, right? VLB. As a matter of fact, you can write Newton's law with it to describe the motion of the bar. This is where physics 1A comes in, okay? Not just 1C anymore. You choosing the downward direction to positive, you get mg minus FB. That is the net force, okay? The net force, sum of the force going in x direction. Okay? Now, shouldn't that be equal to mass times acceleration? MAX. Right? And then, if you elaborate this a little bit, you find mg minus FB, which is BIL. BIL. L is the length. That's from chapter 29. Okay, review that. mg minus BIL. Shouldn't that be equal to mass times acceleration? I can rewrite acceleration as the second derivative of x with respect to time. Right? Okay. Now, initially, there is very slow motion. Okay, because it just started from rest. The motion is pretty slow. So you do not cut through the field lines quickly. And if that is the case, you do not change the flux quickly. And therefore, there is not too much of an EMF. If there is not too much of an EMF, do you think there will be a large current? Of course not. The current will be very small. So very small current, therefore, the magnetic force will be small. Okay? So initially, the magnetic flux is very small. In fact, at t equal to 0, it starts as 0. So at that very moment, when you just get the thing going, at that moment, it is still a free fall. Okay, so V should increase at this rate. The slope will be equal to G. But gradually, as you increase the cutting speed, you're going to increase the induced current. As a result, what happens? Well, the downward force remains mg. That never changes. The upward force is now greater and greater. So that makes the net force going downwards smaller. Right? So as a result, the acceleration will be falling less than g. All right. So the acceleration would taper off. It's going to be like that. As a matter of fact, at some point, v will reach a saturated value, which we know exactly what it should be, because as v gets greater and greater and greater, the current is so large that the magnetic force caused by this induced current exactly cancelled with mg. Okay, the net force is what? 0 on the bar. And can the speed still change? Not anymore. That's why we say it reaches saturated value. That will be V maximum. Okay, V maximum. So V should go up like that. Qualitatively, we say it should go up like that. And one can actually find out what that V maximum is. Okay, what that V maximum is. How do you do that? Well, at V equals V maximum, that is when AX equals 0. Right? There is no acceleration anymore. So mg would be equal to what? BIL. But wait a minute. I know what I is. I is, I'm going to copy B and L. I is EMF over R, isn't it? Ohm's law, right? I mean, this. Look at this circuit. It's really just powered by a battery. It's not a real battery, but it's just behaves just like a battery. Okay, this bar behaves like a battery. It drives a current I through a resistor R. Therefore, it's I is epsilon over R, right? And we know what exactly epsilon is. Epsilon is BLV. Okay, BLV. Please do not confuse BIL and BLV. Okay, BIL is the magnetic force on a current of length L, and BLV is the EMF generated as a metal bar of length L cuts through the magnetic field lines the speed V. It's a different deal. But anyhow, mg equals BL over R times BLV. I can solve for that V here. That V is equal to mgr. mgr divided by what? V squared L squared. That in fact is V maximum. Right? V maximum. Because when V equals that value, V maximum, there is no acceleration. You must have reached the final saturated value of the speed. The speed can no longer increase anymore. Alright, this is the final speed. We will solve the entire problem. We'll look at the entire curve and we will see whether or not our general complete solution predicts the same result when t approaches infinity, when V goes to V maximum. Okay, but you know, we have a qualitative understanding what's going on now. Qualitative understanding, right? The speed of the bar should rise like that, and it should reach a saturated value. Now, let us go one step further. Let us try to solve this equation. Okay, let's solve this equation so that we can actually find the entire curve, not just where it starts, where it ends. Okay, we're going to plug this. We're going to plug this expression of BIL into here. Okay, BIL, as you know, equals B squared L squared V over R, right? Because you go from here to there, it's Ohm's law, and go from here to there, it's just motional EMF. Now we cannot use V maximum, we can simply use V, because we haven't necessarily reached the final value yet. So I'm going to write down the equation by plugging this this expression into here. This is mg minus, instead of BIL, I'm going to write B squared, okay, L squared over R times V, not V maximum, because it doesn't have to be maximum until t equals infinity. The other side, I can either write m times second derivative of x with respect to time, or I can write dv over dt. Okay, either way is fine. So this is the differential equation that I need to solve, and let's see how we might solve it. Now, it's a rather simple differential equation. In fact, you can do it with a separation of variable again. dt is the only place where t shows up explicitly. I can simply solve for dt, put it on one side and put all the v's on the other side and integrate both sides, which I can easily do. It's kind of boring. So what I would do is, just like what I did for the RC circuit, charging, discharging, I'm going to use my physical intuition first to sort of guess what the answer should be, and then see if it makes sense. Okay, now, you know the speed of the bar should increase like that, right? It should start from 0 and will end up at V maximum. And this function reminds us of what? Of the charging cycle of an RC circuit, right? So you remember what that expression looked like? It's like 1 minus e to the negative t over tau, and the whole thing times either V maximum or Q maximum. Remember that? Okay, something similar. Can we get something similar here? Well, take a look at the math. Take a look at the math. Even if you didn't learn how to solve this type of differential equation in your math class, it's still quite simple to see. If you move this term to the other side, what's so special about this equation? You see, the left-hand side is just mg. Okay, it's just a constant, never changes over time. The right-hand side, on the other hand, is the sum of these two terms, and both of these two terms do change with time. As time changes, v changes, so does dv/dt. And yet, you add them together, you find you get a constant. Now that means, however v changes, however it changes with time, dv/dt should change with time in the same manner, so that they can always add up to a constant, right? For example, this rules out the possibility of v becoming a power function, because v is equal to, say, t to the power 6, then dv/dt will be equal to t to the power 5, and you add them together, you are not going to get a constant for all t. You see? Okay, so the question is, what kind of function is such that when you take a derivative, you get its own time dependency back? Well, of all the elementary functions, there is only one function that behaves like that, right? And that's the same old, what? Exponential function. Okay, so we can expect something like this, something like e to the negative alpha t. Why negative? Because if it's a positive sign, then it's going to go out of bound. It goes to infinity as time approaches infinity. How? Okay, now let's see. Let's see if that works. Okay, e to the negative alpha t is a function that starts from 1 and ends up at 0. It's like that. But we want the speed to increase, not to decrease. We want to flip that curve up, right? So what I'm going to do is I'm going to flip it up like this by giving a negative sign. Okay, so I'm going to give it a negative sign, so it's negative e to the negative alpha t. That function actually increases, not decreases. But that function goes from negative 1 to 0. I wanted to go from 0 to 1, so I'm going to add the whole 1 here. Right? It's like we did for the RC circuit. That combo goes from 0 to 1 as time approaches maximum, which is infinity. But I want the function v to go from what? To 0 to v maximum, not to 1. So therefore, I'm going to multiply this whole thing by v maximum. There we go. Then my question is this the actual solution? Is this right? Is v equal to that? That is my trial solution. How do you know whether it's right or wrong? There is only one way to know for sure, and that is what? I'm going to plug that in, okay? I'm going to plug that in to see if I get the correct result. See if it actually solves the equation. Okay, let's do that. Okay, let's work out the algebra together. I'm going to plug this trial solution into the equation. And what's the first term? The first term is just mg. Okay, it never changes. mg. The next term is what? Minus b squared L squared over r times v, which is this. V is now this, right? So it's v maximum 1 minus e to the negative alpha t. The other side is m dv/dt. So it's m, copy m dv/dt. Take a derivative, okay? Take a derivative. That one is gone. Negative negative cancels. V maximum alpha e to the negative alpha t. Okay? Now, here. There are two terms that are time variable. I'm going to move both terms to the right-hand side. Keep everything else on the left-hand side. So on the left-hand side, I have this and I have this. So you get mg minus v squared L squared v maximum over r. That's what I have left on the left-hand side. Two constant terms. Okay? And on the right-hand side, I have this guy and I have this guy. Let me take the common factors out. E to the power negative alpha t. And there's a v maximum both here and there. V maximum. Okay? And then what I have left. Here is m. And there's an alpha. Right? That completes this term. And then I'm going to move this guy over. Negative negative cancels. I get a negative sign after I move. V maximum is already out. B squared L squared over r. That's what I should keep inside. Okay, now what? You see, there was a reason why I took both time variable terms to that side. Because now, the right-hand side is time variable, and yet the left-hand side is a constant. See, this is a constant, right? This is a constant. It never changes. The only time variable part is e to the negative alpha t. In fact, that is a constant too. how can the left-hand side be a constant and yet the right-hand side be time variable as t changes? That doesn't work unless what? You kill it, okay? You say this factor is simply 0. So no matter what t is, no matter how e to the negative alpha t changes, the right-hand side is a constant, which is 0. Okay, but if you do that, you have no choice but to leave this guy 0 as well. So you see, now you kill two birds with one stone by assuming that both sides must be time constant, must be independent of time. Okay, you get a 0 here, 0 there. That gives us two equations, one of which will give us V maximum, the other will give us alpha. Okay, now let's see. Set this to equal to 0. mg equals b squared L squared Vm over r. Therefore, V maximum equals what? mg r over what? B squared L squared. Okay, that is the requirement of this to be 0. But you see, that is exactly in agreement with what we got. We got that without all this detailed math. We got that by assuming the net force has to be 0 as time approaches infinity. That's how you reach a saturated speed. That's when the acceleration is 0. Newton's second law. Okay. Now the other equation I must observe is that that has to be 0, and that tells me what alpha is. So alpha equals what? B squared L squared over mr. See? So I have successfully solved this equation. Okay, in its entirety. This trial solution is in fact correct. All I have to make sure is V maximum equals that and alpha equals that. Okay, so here's my complete solution. V is a function of t equals V maximum, which is mgr. I'm sorry, you have to see it. mgr b squared L squared, and then 1 minus e to the negative alpha t. Here's alpha right here. B squared L squared over mr times t. This is the complete solution to this problem. Okay, quantitatively V goes up like that. Okay, it flattens out. Now, before we go on to the next problem, let's take some further look at the solution to see if it makes sense. Okay, to see if it makes sense. You know, first of all, qualitatively, it's a curve like that which matches our intuition. But V maximum equals this. Is this? We know it's from the math, right? From Newton's Newton's second law, that sort of thing. But is it qualitatively understandable? You see here, V maximum will be large if there is a large mass, a large resistance. Will be small if there is a large magnetic field and large length of the wire. Does that agree with your intuition? No. Look at the diagram again. Okay, look at this diagram here. If mass is large, you have a very heavy rod, right? If it's a very heavy rod, then that means gravity is more important, right, on the heavy one. For the same magnetic field, it cares less, right? The magnetic effect is not that important. That means it can accelerate longer under the influence of gravity, because gravity dominates for a very heavy object. Therefore, V maximum could be greater. That makes sense. Okay, now, what about R, the resistance? Here it says a larger resistance R will give you a greater final speed. Does that make sense? Okay, a larger resistance, if everything else is the same, a larger resistance will mean what? Mean the current will be smaller, right? For the same EMF, right? For the same cutting, the current will be smaller. If the current is smaller, that means there is a smaller amount of upward magnetic force which counteracts with gravity, right? And doesn't that mean that gravity is greater by comparison? Because FB, the magnetic force, is comparatively smaller now. So effectively speaking, I have greater amount of gravity, and therefore I can go faster. I can reach a greater speed. See, it makes sense. Okay, now what about B and L? Well, a large B means you have a large magnet. Well, the greater magnetic field means the magnetic effect, of course, plays a greater role, and then you have a greater magnetic force, which will further limit the downward speed. So you get a smaller final speed. And of course, a larger L has a similar effect. You are using a longer bar to cut through the magnetic field lines. You cut through more field lines as you drop by the same distance because the bar is longer, and therefore you amplify the effect of due to Faraday's law, because you cut more field lines. EMF is greater. Okay, that drives a greater current and therefore greater upward magnetic force to limit the speed. So everything makes perfect sense here. Now, alpha. Alpha is a constant which has a unit of 1 over time. Okay, a large alpha means what? Means the speed quickly reaches a saturated value. So it goes up like that. Okay, quickly reaches saturated value. And a small alpha means it takes a long time for V maximum to be realized. Now remember, the reason why there is a V maximum in the first place is because there is a magnetic effect, Faraday's law. Without Faraday's law, it's a free fall. V maximum will be infinity. It would never ever be reached. It keeps on going and going and going and going. Okay, so when alpha is large, you will have it will quickly reach a saturated value. That is very unlike free fall. That means that is when the magnetic effect is more important. Okay, Faraday's law is more important. And that happens when you would have a large magnetic field, a long bar, and a small resistance, which amplifies the current further. Okay, see if that makes sense? Look at alpha. Large magnetic field, long bar, and a small resistance. Does not all these things make alpha greater? Greater alpha, again, means it is very unlike a free fall. Okay, so that it makes sense. Now you can also think of what happens to the mass here. If the mass is small, that means relatively speaking, gravity is not very important, or in comparison, magnetic effect becomes more important. So that makes the bar reach saturated speed even quicker, and therefore alpha should be greater. So everything makes perfect sense here. Okay, now we're not even done with this problem yet. I want you to focus on one more thing here. That is the energy transfer process. Okay, if you believe in conservation of energy, which I'm sure you do, then you must make sure the energy is actually properly balanced. Okay, look at what happened over a certain unit time, or dt. During that time, gravity did some work, obviously. Gravity did some work, and that work, part of that work should go to increase the kinetic energy. In fact, 100% of that will be increasing kinetic energy if there were no magnetic force present, right? So it will be just a free fall, right? Now, what happens when there's a magnetic force present? The magnetic force would then reduce the kinetic energy of the bar, but what does that extra kinetic energy go? It will become what? The thermal energy that's dissipated on the resistor. Okay, so what does the conservation of energy tell us? It says that, okay, if you want to balance the energy in this process, the power delivered by the gravitational force, that will be the force of gravity mg times the speed v, right? That should go two ways. One of which is to increase the kinetic energy at a certain rate, dk dt. Okay, so you know, do work, the power delivered per, that's the work delivered per unit time, that's power, should become dk dt, and the other part should be the power dissipated over there on the resistor, I squared times r. That is the requirement for the conservation of energy. Okay, is this right? Is this actually correct? Well, let's see. What is dk dt? dk dt is just ddt of 1/2 mv squared. So you get mv dv dt. That's what it is. Right? So it says mg v equals this, plus then I squared times r. Now I know what I is, don't I? The current, okay? The current is epsilon over, okay, here. I is epsilon over r, and epsilon is b, what is it? BLV, isn't it? So BLV over r. So I squared is b squared, L squared, v squared over r squared. That's I squared times r. So the question is this right? That is the requirement for the conservation of energy. Okay, conservation of energy. Requires that. Well, see, if you cross 1 power of v for every term, v, v, and v, what do you get? You say, you will see that mg equals to m dv dt plus b squared L squared v over r, right? But is this right? Well, guess what? This is exactly the same as the equation of motion that we obtained earlier. See that? See that? See that thing here? All you have to do is move this guy over, and you will see that these two expressions, sorry, I don't have space for you to see both of them simultaneously. This thing and that thing are really exactly the same. Okay, this is the equation of motion, F equals ma. This is a requirement from conservation of energy, and guess what? They match each other. All you have to do is move this term over to that side, you get that. Okay, so our process does observe conservation of energy. Please keep that in mind as well. This is a very comprehensive problem. We took a lot of time going over that. So please make sure you understand every aspect from force point of view, from energy point of view, and that you can learn a lot from this very just one single example. Teaches you a lot of things about